Optimizing deep learning models for time series forecasting using GridSearch. The use of GridSearch is typically not feasible in deep learning techniques. Deep learning techniques usually demand considerable volumes of data and complex models, causing the models to take several hours, days, or even weeks to complete the training process. GridSearch can be utilized to adjust the hyperparameters of a deep learning model in situations where the datasets are smaller, like univariate time series. This tutorial will guide you through the process of creating a framework for grid searching hyperparameters in deep learning models. By the end of this tutorial, you will possess knowledge. In order to optimize model hyperparameters, it is important to have a generic grid searching framework in place. This article will discuss the steps to develop such a framework. How to perform a grid search for hyperparameters on a multi-layer perceptron model for predicting the number of airline passengers over time. Modifying the framework for utilizing grid search hyperparameters in convolutional and long short-term memory neural networks. The dataset, monthly airline passenger, presents the total number of international passengers in thousands for an airline from 1949 to 1960 on a monthly basis. Transform the language in this passage. Keep the document under the name monthly-airline-passengers.csv in your present working folder. To utilize this dataset as a pandas series, we can employ the readCSV function. Subsequently, we can provide an overview of the dataset's structure to identify the total number of observations. Afterward, a line plot can be generated for the series in order to understand its structure. All of this can be tied together. The example provided below is complete. The initial step of the example is to display the dataset's structure. The data is collected on a monthly basis for a period of 12 years, resulting in a total of 144 observations. We will be utilizing the most recent 12 observations, equivalent to the past year, as our test set during the testing process. The creation of a line plot begins. The data clearly shows a pattern and follows seasonal changes. The seasonal component lasts for 12 months. During this tutorial, we will discuss the tools used for grid searching. However, we will not be optimizing the hyperparameters of the model for this particular problem. Instead of discussing a naive model, we will illustrate how to perform a grid search for hyperparameters in deep learning and identify models that show promising performance. Based on previous trials, a simple model can yield a root mean squared error, also known as RMSE, of 50.70. Keep in mind that the units are thousands of individuals, by retaining the value from 12 months ago, indexed as 9-12. This unrefined model's performance sets a limit for a more competent model in addressing this issue. Any model that demonstrates a predictive performance below 50.70 for the previous 12 months is considered to have skill. It is important to mention that a calibrated ETS model has the capability of reaching an RMSE of 17.09, while a calibrated SARIMA can attain an RMSE of 13.89. These set a minimum expectation for a well-configured deep learning model for this issue. After establishing the problem and setting expectations for model proficiency, it's time to consider the construction of the grid search test framework. In this segment, a grid search evaluation system will be constructed to assess a variety of hyperparameters for diverse neural network designs, including MLPs, CNNs, and LSTMs. This portion is separated into the subsequent segments. Splitting data into training and testing sets. Supervised series. Supervised learning can be thought of as a series. The process of walk-forward validation. Validation using walk-forward technique. Evaluate again. Performance can be summarized as the measure of success and effectiveness in achieving desired goals and objectives. It is the evaluation of an individual, group, or organization's actions and outcomes based on set criteria. Performance can impact overall productivity and success, and is often used to identify areas for improvement and make necessary changes. Example of a completed task. To begin, divide the loaded series into two separate sets, the train set and the test set. For the training phase, we will utilize the initial 11 years, 132 observations, while the remaining 12 years will be used for the test set. The function train test split below divides the series, using the raw observations and the desired number of observations for the test set as parameters. Afterwards, we must have the capability to convert the single variable sequence of data into a supervised learning task in order to effectively train neural network models. When data is divided into multiple examples for the model to learn from and generalize across, this is known as a supervised learning approach for a series. Both an input component and an output component are required for each sample. The input component will consist of a certain number of previous observations, like 3 years or 36 intervals. Our focus is on creating a model for one-step forecasts. Thus, the output component will represent the overall sales for the upcoming month. This can be achieved by using the shift function on the pandas data frame. This function enables us to move a column either downwards, towards the future, or upwards, towards the past. By treating the series as a column of information, we can generate several duplicates of that column, adjusted to correspond with different points in time. In this way, we can compile the necessary input and output elements for our samples. Shifting a series downwards results in the introduction of NaN values. This is because we lack values beyond the beginning of the series. For instance, the sequence defined in the form of a column. This column has the capability to be moved and added beforehand as a column. Upon examination of the second row, it is evident that the value 1 is given as input and observed in the previous time step. Additionally, the following value in the sequence 2 can be forecast or acquired by the model to be predicted upon presentation of 1 as input. Rows containing NaN values can be eliminated. The function series to supervised below implements this functionality, enabling you to indicate the number of past observations to include in the input and the number to include in the output for each sample. This action will also eliminate any rows containing NaN values, as these cannot be utilized for training or testing a model. One way to assess time series forecasting models is by implementing walk-forward validation on a test set. Walk-forward validation is a technique in which the model predicts the outcome for each data point in the test set individually, in a sequential manner. Once a forecast has been made for a time step in the test dataset, the corresponding true observation is included in the dataset and can be accessed by the model. Less complex models can be adjusted with the observation before making the next prediction. Rephrasing. Due to their significantly higher computational expense, complex models like neural networks are not retrained. However, the actual recorded data from the current time step can also be utilized as an input for forecasting the following time step. Initially, the dataset is partitioned into two sets, the train set and the test set. To execute this division, we will utilize the train-test-split method and input the predetermined amount of data to be utilized as the testing set. A configurations training dataset will undergo one model fitting. A general model fit function will be created to carry out this task, which can be customized for the specific type of neural network we may need in the future. The performance of the model can be enhanced through the model configuration and the training dataset. Once completed, the model is prepared for predictions. Every time unit in the test dataset is sequentially listed out. The fit model is utilized to make a prediction. Once more, we are going to create a universal function called model predict, which will require the fitted model, the history, and the model configuration in order to generate a single prediction for one step. The forecast is appended to a collection of forecasts, while the actual observation from the testing data is added to a roster of observations, which was initially populated with all observations from the training set. The list expands as the walk-forward validation progresses, enabling the model to make a prediction for one step by utilizing the most recent historical data. After making all of the predictions, the results can be compared to the actual values in the test set, and an error measurement can be computed. The RMSE, or root mean squared error, will be computed by comparing the predicted values to the actual values. The root mean squared error, RMSE, is obtained by taking the square root of the mean of the differences between the predicted values and the actual values, all squared. The function measure RMSE uses the mean squared error function from scikit-learn to compute the mean squared error, also known as MSE. It then takes the square root of this value. Listed below is the walk-forward validation function, which integrates all of these components together. The process involves obtaining the dataset and selecting the desired number of observations to serve as the test set. Along with this, the model's configuration is also specified. The outcome of this setup is then the RMSE value, which indicates the model's performance on the test set. Stochastic neural network models are utilized. This implies that, with an identical model setup and training data, every time the model is trained, a distinct set of internal weights will be produced, subsequently influencing its performance. One advantage is the model's ability to adapt and discover effective configurations for intricate problems. This can pose an issue in both assessing a model's performance and determining the most suitable model for making predictions. In order to assess model performance, we will repeatedly evaluate a model's configuration using walk-forward validation and calculate the average error from each evaluation to report the overall error. This may not be achievable with larger neural networks and may only be feasible for smaller networks that can be trained within a few minutes or hours. The function repeat_evaluate is defined below and lets the user specify the number of repeats as an optional parameter with a default value of 10. It calculates the average RMSE score from all repeats and returns it. The framework is now complete with all its components. The only remaining task is to create a function that will control the search. One option is to create a GridSearch function, which requires the dataset, a collection of configurations to explore, and the size of the test set for conducting the search. After calculating the mean scores for each configuration, the list of configurations is organized in ascending order to display the top scores first. Below is the complete function. With the test harness elements properly defined, we can now bring them together to establish a basic persistence model. The model fit function will not be applied as there is no requirement to fit a model. Instead, it will just yield none. We will specify a list of index offsets in the past observations relative to the forecast time using the config to inform the prediction process. For instance, the observation 12 months ago minus 12 will be utilized in relation to the time being predicted. The implementation of the model predict function can utilize this setup to permanently store the value at the offset that is negative relative to the current position. The model is assessed 10 times for each configuration. However, since there is no randomness in the model, the score remains constant with each evaluation. The top 3 performing model configurations, along with their corresponding RMSE values, are reported at the conclusion of the run. As anticipated, the persistence model yielded the strongest performance by retaining the value from 12 months prior, relative offset minus 12. With the implementation of a strong test platform for grid searching model hyperparameters, we are now able to assess a group of neural network models. There are numerous components of the MLP that may require adjustments. We will outline a basic structure comprising of a single hidden layer and establish 5 hyperparameters to customize. The following parameters will be used in this model: n input, n nodes, n epochs, n batch, and n diff. For n input, the number of prior inputs to be used will be specified, e.g. 12 months. N nodes indicates the desired number of nodes in the hidden layer, e.g. 50. As for n epochs, the number of training epochs will be defined, e.g. 1000. The number of samples to include in each mini-batch will be determined by n batch, e.g. 32. Lastly, for n diff, the difference order will be specified, e.g. 0 or 12. It is worth mentioning that modern neural networks are capable of handling raw data with minimal preprocessing, such as scaling and differencing. However, when dealing with time series data, there are instances when differencing the series can simplify the modeling process. Remember that differencing involves manipulating the data by subtracting the value of a previous observation from the current one, thereby eliminating any trend or seasonal patterns. The GridSearch test harness will now incorporate support for differencing in the event that it benefits your individual problem. This dataset does provide value for internal airline passengers. The below function, difference, will find the difference of a specified order within the dataset. The option to use differencing is available with a value of 0, indicating no differencing is needed. However, if the order is 1 or 12, the data must be differenced before fitting the model. Additionally, the predicted values from the model will need to have the differencing undone before being returned as a forecast. The steps needed to incorporate the MLP model into the test harness can be outlined as follows. There are several steps we need to take to unpack the list of hyperparameters. To begin, the list of hyperparameters must be unpacked. This involves a series of steps that must be followed. Afterwards, it is important to get the data ready by performing a series of steps, such as differencing, transforming it into a supervised format, and separating the input and output components of each data sample. We can proceed to define and apply the provided configuration to the model. The following is the full code for the implementation of the model fit function. The selection of 5 hyperparameters is not the sole or optimal approach to adjusting the model. There is an option to adjust additional parameters within the function, including the inclusion and dimensions of hidden layers, among other possibilities. After the model has been properly fitted, we may utilize it to make predictions. If the data has been transformed, the opposite transformation must be applied to predict the model. To complete this task, the value predicted by the model is adjusted by adding the value at a relative offset from the history. This also implies that the history must be adjusted to match the expected form of the input data used for the prediction. After being prepared, the historical data can be utilized to generate a sole sample that will serve as input to the model for making a prediction for one step. The dimensions of each sample should be 1 n input, with n input being the desired amount of lag observations to include. Ultimately, a forecast can be formulated. Below, you can find the full code for the model predict function. We must now establish the scope of values to experiment with for every hyperparameter. A list of parameter combinations to experiment with can be generated using a function called model configs. To illustrate, we will establish a limited number of configurations for testing, such as a 12-month difference, that we anticipate will be necessary. We highly encourage you to explore standalone models, analyze learning curve diagnostic plots, and apply domain knowledge to define parameter ranges for grid searching. It is encouraged to conduct multiple grid searches to refine the ranges of values that display enhanced performance. Listed below is the implementation of the model configs function. With all the necessary components in our possession, we can proceed with grid searching MLP models for a univariate time series forecasting task. The framework can now be modified for performing grid search on CNN models. One can search for a similar set of hyperparameters as the MLP model, except the number of nodes in the hidden layer can be substituted for the number of filter maps and kernel size in the convolutional layers. The selected group of hyperparameters for the CNN model grid search are as follows. A few extra hyperparameters. Number of previous inputs to be used as the model's input, for example 12 months. The convolutional layer contains a specific amount of filter maps, typically represented as n filters, for example 32. Convolutional layer, the size of the kernel used in the layer, e.g. 3. Number of training epochs, the total number of training epochs, typically expressed as a numerical value, e.g. 1000. N batch, the amount of data to be included in each mini-batch, typically 32 samples. Rewritten, the order of difference, E0 or 12. There are several supplementary hyperparameters that you may want to explore. These include incorporating 2 convolutional layers followed by a pooling layer, repeating the pattern of convolutional and pooling layers, implementing dropout, and other options to consider. We're going to construct an uncomplicated CNN design comprised of a singular convolutional layer and a single max pooling layer. The data should be organized similarly to how it is done for the MLP. The 1D CNN model differs from the MLP in its input data requirements. While the MLP expects the data to have the shape samples, features, the 1D CNN model requires samples, time steps, features, with features mapping onto channels. In this particular case, the value of 1 is assigned to represent the single variable measured each month. Below is a listing of the full implementation for the model fit function. Predicting with a well-trained CNN model is similar to making predictions with a well-trained MLP. The only variation is that the input data must have a 3-dimensional shape consisting of 1 sample. Below is the complete code for the implementation of the model predict function. Ultimately, we can establish a compilation of setups for the model to assess. Similar to previous methods, this task can be accomplished by creating a compilation of hyperparameter values to experiment with, which will then be stored in a list. In order to achieve a timely execution, we will experiment with a limited number of configurations. The following is the complete listing of the model configs function. All the necessary elements are now available for conducting a grid search on the hyperparameters of a convolutional neural network designed for predicting univariate time series. The framework for grid searching the hyperparameters of an LSTM model can now be implemented. The 5 hyperparameters for the LSTM model will remain consistent with those of the MLP, and they are number of previous inputs to be utilized as model input, e.g. 12 months. Number of nodes to utilize in the hidden layer, e.g. 50. Number of training epochs, e.g. 1000, n epochs. The value for n batch specifies the number of samples that will be included in each mini-batch, such as 32. Change in sequence, the order of variation, e.g. 0 or 12. We are going to create a basic LSTM architecture consisting of 1 hidden layer and the number of nodes, determining the amount of units in this particular layer. Tuning additional configurations, such as utilizing a bidirectional input layer, implementing stacked LSTM layers, or even merging with CNN or conv-LSTM input models, could prove intriguing to investigate. The LSTM model, like the CNN model, requires the input data to have a 3-dimensional structure consisting of samples, time steps, and features. Similar to CNN, the individual input instance utilized for forecasting must also be reformatted to match the anticipated 3-dimensional configuration. Listed below is the fully functional model predict function. We have the ability to establish the function that is utilized to generate the roster of potential model setups to assess. The training process for the LSTM model is comparatively slower than the MLP and CNN models. Therefore, it is recommended to assess fewer configurations per run. We will introduce a basic pair of setups for investigation: random and grouped gradient decline. We have now collected all the necessary components to perform grid search on the hyperparameters of the LSTM model used for single variable time series prediction.